They are in my office. You can come and pick them up if you'd like to. Yes. Although, well, right. I will be, oh, I guess it's time. Hello, welcome. Let's see, lots of stuff to catch up on. As you know, last Friday we took exam 1. So that all has been graded over the weekend. Let me show you the damage that was done. Okay, I have posted in the week 5 module an image, which is a histogram. Here's what it looks like. Oh, I'm not sharing for the Zoom people. Hold on, let me start sharing for the Zoom people. And you're not seeing this up here either, so nobody's seeing this. Just in case anybody's wondering, nobody has yet seen what I'm showing. Not that there's anything real exciting here yet. So that's gonna come up here, and now this is gonna come up. Okay. Now, what were we looking at? This is what we're looking at. The histogram of scores for exam 1. So there was out of 50 points altogether. There wasn't a 50, I think 48 was the highest score. There's a pretty nice distribution of scores, a little more down here in this tail than I would like, but the overall average was a 38.65 out of 50, which gets us to about 77, which is pretty good for a physics exam. So I'm not at all displeased with that. I went to pass them back to your mailboxes and realized that you don't have mailboxes. Perhaps because of COVID, I have not actually looked into why you don't have mailboxes, or perhaps because Jamie hasn't been here for the past month much. But they are all in my office. You can come and pick them up. If you did not take it online, I have a physical copy in my office. You should stop by sometime and pick it up. They're actually laid out on the desk. You don't even have to talk to me if you don't want to in my outer office. So you can go find yours, grab it, and take it home. One other thing that I wanted to announce today, and that is I have made a slight adjustment to the grade distribution in the syllabus, because I haven't been asking any participation credit questions, and I think that it's kind of unfair this semester to ask for participation credit. So I've decided to remove that 4 points out of the total grade credit in the syllabus, and I have redistributed those 4 points to a combination of homework for 2 of them and exams for the other 2. So that is the change that I made. I uploaded a new version of the syllabus. You can go to the syllabus and see. This used to be 4, this used to be 64, this used to be 28. So I've just revised this a little bit. There's a new PDF. If you want to go download that, you can. It should be, and you can see in red the places where I've made some slight changes. Shouldn't affect much. I just didn't want people worrying about not being here, and I'm going to start asking top hat questions. I encourage you to answer the top hat questions. I think it'll be helpful for me to know what you're answering. I think it'll be helpful if you're new to know what you're answering, but there will be 0 grades tied up in any of that. Okay. Questions about exams or syllabi or grading distributions? I think the grades that are on Canvas now should be current. I don't think there's anything that's missing there. So go on and see, take a look. Okay, great. So we're starting a brand new topic. And that topic is fluids. Kind of every single topic we're doing this semester is a 2 to 3 to 4 week preview of a class, of an entire class that you would take as a junior or senior, 300 level class. We've just come off of talking about E&M waves, and that's a pretty good precursor to our electricity and magnetism class that you would take as a junior. Although like, talking about obviously expanding that to much more interesting topics than we've already talked about. Fluids, we're going to spend a couple weeks talking about fluids. And there is an entire 300 level class on fluid dynamics, which again, will cover all of this stuff in way higher detail and then go into other cool stuff as well. Thermodynamics, our next section, sort of the same thing. Every unit we're doing is a preview of an entire class that you could take as a 300 level elective. So yeah, you're seeing that. Okay, so what is a fluid? If I were to force you right now to write down a definition of a fluid, what would it be? A state of matter other than a solid. That's interesting. How would you define solid? A substance that takes the shape of whatever is containing it. So, for instance, I've got a little jar full of water here. I think we could all agree water is a fluid. Okay, good. And certainly it is taking the shape of the container it is in, at least at some level. It's not taking the, if there was some interesting shape at the top, it wouldn't be taking the shape of the top of that container. But that's not a bad definition. In fact, if I were forced to make a definition, it would probably be something similar to that. A fluid is a substance that conforms to the container that you put it in, the bounds of the container you put it in. I don't think that's what okay, you can write that down, but I think an actual physicist definition would be something that cannot withstand shear forces. That's a good physics definition of a fluid. This desk can withstand shear forces. I can push it on one side and it's not going to deform. If this table were made of water, it wouldn't be able to do that. I would push it and it would collapse into a puddle on the floor. Even if I didn't push it, it would collapse into a puddle on the floor. So colloquially, when we say fluid, certainly we mean things that are liquids. In physics, we really mean, your definition is not a bad one, gases and liquids both fit the definition of fluids. If I were to empty the water from this container and put gas in it instead, like air, it would in fact conform to the shape of this container, and it would not be able to withstand shear forces either. So there's a big difference though between, why isn't this getting signal? That's very interesting. Is that the problem? Maybe that's the problem. Yes, that's the problem. Okay, we're good. There's a big difference between the fluid in this container and the fluid that's in the air around us. And that is the compressibility of the fluid. Water is a nearly incompressible fluid. It is very difficult to change its density. You have to really, really push on it to change it at all. So you can think of it as an incompressible fluid. Air is really easy to change the density. It's a very compressible fluid. That makes things harder and more difficult to understand. So for this 2-week unit, 2-week plus unit on fluids, we are going to be thinking only of incompressible fluids. And so when we say fluids for the next 2 weeks, we're going to be talking about water. We're going to be talking about oil. We're going to be talking about liquids in general. But most of the things that we're doing are more general than that. There will be certain things that aren't applicable to compressible fluids, and we'll sort of talk about them, and I'll point them out as we go. This is a case where the requirement that we're doing compressible fluids is important. Okay, so let's oh, yeah, we should do that, shouldn't we? I'm actually, thank you for reminding me. See, I get rid of top hat and it's just dead. It's gone. Actually, okay, so let's do a check-in. For those of you, again, this is only for people who are here. For the dean's office knows who is here. The code is 5343. Thank you. Okay. So some of this stuff that we're going to be doing is going to look a lot like Analyt 1. It is dynamics at some level. We're going to be talking about forces. We're going to be talking about masses. We're going to be talking about accelerations at some level. We're going to be talking about things like that. But there's going to be some fundamental differences. So this is sort of a new branch of physics called continuum mechanics. So in Analyt 1, you are always thinking about point particles. Even if you talked about a ball being shot out of a cannon, you were really talking about a point mass at the center of that ball moving through some regional space and having forces acting upon it. So we have some nomenclature that you've built up over the past years on point particles. And we need to think about how we want to think about those same concepts in this new continuum mechanics. So for instance, you can talk about the mass of a point particle. You can talk about the force on a point particle. Those are things that aren't as relevant specifically to a fluid, right? The mass, the total mass of the fluid inside this jar is not all that useful unless I want to chuck this jar of water at the wall, right? Unless I want to treat it like a point particle. I almost never will want to treat this like a point particle. I'm much more interested in the behavior of the fluid itself, the behavior of the individual elements within the fluid itself. So what can we use instead of mass that would be sort of equivalent to mass that would relate to the fluid as a whole instead of some element of the fluid? Density is exactly what I'm going for. So instead of mass, where we're thinking about the entire mass of something, we're thinking about density. So density, this is again from high school physics or even high school chemistry. We usually use the Greek letter rho to signify density. And this is, you can think of this as a delta M over delta V, where delta M is a change in mass. That's an M. And delta V is a change in volume. Even this is a over complication of the thing. If you're talking about an incompressible fluid, what does that imply about the density of the fluid? It's constant. And so this is a general definition. The deltas are only important if your density can change. If your density cannot change, and you can do a total mass divided by a total volume, and you never have to worry about integrating over anything or doing any weird differentials. Really, it's just mass divided by volume for an incompressible fluid. But this is a more general. So for incompressible fluids, this implies that density is just equal to mass divided by volume, and that this is a constant within the fluid itself. We can take any chunk of this we choose, measure the total mass, measure the total volume, and that gives us the density of the entire fluid as a whole. So again, these may be or may not be things that you're familiar with, but it's useful to build up a general idea of what these density numbers are. Yeah. How common is it for a fluid to be completely incompressible, like unable to be compressed at all? Is that what you asked? Right. Never. There is no true ideal incompressible fluid that I know of. Maybe like the centers of neutron stars or something like that. But I think even that is compressible. In practice, we have fluids that are under normal circumstances in which we would encounter them are basically incompressible. Within our ability to measure it, the density would not change. But that's, again, we're shoving some details under the rug. Those details are pretty inconsequential though for water flowing through pipes, or anything that you would be dealing with sort of at an atmospheric pressure level, or even in the ocean. The density even at the bottom of the ocean is not substantially different than the density at the top of the ocean. In fact, it depends more on what's in the water. Salt water has a slightly different density than fresh water, and that's more important than the density as a function of height. Does that answer the question? Okay. So let's look at some common densities. Liquids and solids, on average, in general, range from about 500 to about 10,000 kilograms per cubic meter. Now, a cubic meter is a really large chunk of volume, right? You're talking about, maybe half the size of this table underneath it. That's a pretty big chunk. You wouldn't be able to pick up a water if this thing were filled with water, right? That's a pretty big chunk of thing. In fact, water, anybody know what the density of water is? Fresh water? It is 1,000 kilograms per cubic meter. In fact, if you do unit conversions, this is equal to 1 gram per cubic centimeter. And this is the original 1795 definition of what a gram was. It is the mass of 1 cubic centimeter of water. That's not a bad rule of thumb to have in the back of your head about densities of things. So this is no longer the way the gram is defined, or the kilogram is defined. In fact, the way the kilogram was defined was just changed in the past couple of years to finally be not based on some actual standard in some vault in Switzerland, but based on some actual units of physical principles. But that's neither here nor there. This still is roughly true. The gram still is roughly defined to be such that 1 cubic centimeter of water has the mass of a gram. And we know what the density of air is? At atmospheric pressure, obviously air is a very compressible fluid, and so you sort of have to talk about density of pressures if you want to talk about densities. In the density of the air in this room is about 1.21 kilograms per cubic meter, or about 1, which is a nice round number. Not exactly 1, it's 20% off of 1, 21% off of 1, but it's to within 1 order of magnitude, it's about 1. Which might be a surprising thing to learn, right? A kilogram is a decent amount of weight. It's probably a little bit more than a kilogram, but not a lot more than a kilogram, right? And this is, my assertion is that the mass of the air in this volume is about the same as the mass of this cup of water. which is interesting because we don't think about having to lift up the air or the air pressing down on us in any way, but it's actually quite a bit of it around us. Okay, there's one more thing in our table that we needed to talk about, and that was force. Again, we're going to think about forces differently than we did when we were talking about point masses. We're no longer interested in the force that is exerted on the fluid, right? I'm not interested, again, if I was interested in the force on the fluid, if I'm chucking it up against this wall, I can revert back to my formulas from Hamlet 1. I'm more interested in the forces that are exerted by the fluid, by elements within the fluid, on other elements within the fluid and its containers and things that it presses up against, for instance. That's really what I'm thinking about. We want force exerted by fluid elements, not on fluid elements. Does it exert a force? Well, I can stick my finger in this glass of water and I'm not feeling great forces, but maybe that's just because the forces are really small, or maybe because something else is going on. But what kind of forces are we talking about? The force exerted by the fluid elements on the other fluid elements and on the container itself. What do we call the forces that are being exerted by fluid elements on other fluid elements? That we refer to such a thing as pressure. So when we're talking about the force for continuum mechanics, we're almost always talking about pressure. So let me go back up and I will write pressure here so you can have it there. And then we'll talk about what we mean by pressure down here. Okay, how do we know it's there? How do we know that individual fluid elements are exerting forces on other individual fluid elements within this container? How do we know that individual fluid elements in this room are exerting forces and pressure on other fluid elements on air in this room? What would, yeah. Right, you're definitely on the right track. If we have, so your point was that each of these elements is sort of stacked on top of one another and must be holding at some level the one above it up. What would happen if there were no forces being exerted by fluid elements on other fluid elements within this bottle? All of these, there's a lot of water molecules in here. They would all fall to the bottom. Gravity wants to push them all to the bottom of this cup, right? We know that there's pressure here because there's some fluid near the top of this cup. If there were no pressure, all of those atoms would be at the bottom. Similarly with the air in this room, if there were no pressure, if there were no forces being exerted by this fluid element on this fluid element, then all of those fluid elements want to go down. Gravity is pulling them towards the floor. All of the air would be on the floor. So it must be that there's some forces being exerted because we are overcoming gravity to have water elements that are above the floor and air elements that are above the floor. Okay, how would we measure it? How do we go about measuring the pressure in a fluid? This is actually trickier than you might think. Here's the actual way that you might want to do it. If you have a device that has a perfect vacuum inside of it, and let's say a spring attached to it, and you put that device in your fluid, you can measure the force on the plate that is being exerted on that spring, right? So this is how a pressure sensor might work. This pressure will cause a force on the plate. I'll come back to the second in a minute. So, so pressure, so put a plate covering a vacuum in fluid, measure force on plate. When you do that, the pressure will cause a force on the plate, and you can measure that pressure by the force that's exerted on that plate divided by the surface area of the plate if P is uniform across the plate. As you can imagine, if you want to get complicated about this, you can break this down into some dot product integral thing, but we're almost never going to have to worry about that in this class. This is pressure equals force divided by area is pretty much as complicated as we're going to make it. Okay, now, however, force is a vector. Question? Yes, the question is, for the Zoomers who couldn't hear it, couldn't we think of this pressure also as the pressure, the force exerted by all of the individual tiny molecules and atoms within the fluid banging up against other fluid molecules and walls and things like that, and just add them all up and get a force and a pressure? The answer is yes, and we are actually going to do that when we talk about thermodynamics in 3 or 4 weeks. So if that's something that interests you, hold on, we will get there this semester. For now, I want to think about this. We can think about pressure even in a macroscopic sense. And that's all I want to think about my pressure is being right now. At its microscopic sense, that's exactly right. What is actually happening, why is it that this water is exerting a force, is because all those water molecules inside there are wiggling around and bumping into each other and the walls. And that's what the force literally is. But it's a macroscopic quantity that is very well behaved as a macroscopic quantity, regardless of what is actually causing it at its root level. So yes, but we're not going to worry about that yet, but we will come back to it. Okay, first I want to think about the vector notations of some of these things that we've written down and whether pressure should be a vector. So let's think about this. Again, let's go back to this picture. In what direction is the force pointing for this particular instrument as we put it in there? Oh, question. Go ahead, finish your thought. Well, just finish the sentence you were just saying. So he was wondering if the orientation of this thing matters, which is exactly the next question I was going to ask. Right. So the point is, if we're talking about this orientation, and the answer to the question I asked, I assume you knew, was the force is pressing down, obviously. There's going to have to be some force pressing in the other direction to keep the spring from compressing completely, which would be the spring force. Those two have to equal each other. You're right. So your point, though, was not only do you have the force of the pressure from the fluid pushing down, you also have the force of gravity pushing down on that plate, because that plate has to have some non-zero mass. Is that your point? You're right. We are going to ignore that particular fact. And we're going to assume that the mass, that this is a very small sensor, and the mass of that plate is practically negligible compared to the forces that are pushing on it from other directions. So my next point was going to be, if you turn this sideways, as you just pointed out, you will get a slightly different force because there's a slight, the mg is no longer pointing with the thing, it's pointing against the thing. But if that's small enough, it's going to be an indetectable difference. And so let's ignore that particular detail. Okay? If we turn this thing sideways, what direction is the force going to be pointing? The opposite direction. So we're pointing into it. We turn it 180 degrees, the force is going to be pointing up. In other words, it doesn't really matter what direction we put this thing in and what direction that vector is pointing. We get the same minus some very small difference correction that we'll have to make for the mass of the plate. We should get the same reading no matter what direction we orient this particular probe. So that is my argument for why P does not need to be a vector. P is a scalar quantity that, in fact, well, this is it comes out of the math too. Let's think about the math. If we were to make these actual vectors, F is a vector and A is a vector, right? So we would really say F equals P times A, and then P must be a scalar. That's the only way that works. If you change the orientation of that sensor, you're changing both the direction of force in A, but P doesn't change, and the value of P doesn't change. So P, bless its heart, is a scalar. It doesn't need to worry about what direction it points in. It points in all directions. This pressure is a force that is exerted by every fluid element on every other fluid element, regardless of the direction that it's in. So I really don't, I mean, this is right, but I'm never going to think about this again. I'm going to think about F is the magnitude of the normal force. And A is the area of the surface of contact. Okay, what are the units on P? This is my sort of triangular bracket notation to mean units of. I think I may be the only one who does this, but it's useful for me. So the units on P are the units on force divided by the units on area. This is newtons per square meter. Obviously, there has to be this has to be named for some famous physicist of yore. Does anybody know which physicist that is who gets the distinction of having the Newton per square meter named after him? It is Pascal. So 1 Newton per square meter is equal to 1 Pascal. Or if you like your 2-letter or 1-letter abbreviations, capital P lowercase a. And this is named after Blaise Pascal, who in the 1600s did pioneering work on hydrodynamics. Okay, so anybody know what the air pressure is in this room in pascals? Go ahead. It's about 10 to the 5. It's about 100,000 pascals, the air pressure in this room. Every fluid element in this room is exerting 10 to the 5 pascals of pressure, newtons per square meter, on every other fluid element in this room, and on this table, and on this whiteboard, and on that screen, and on our skins, and on our eyes, and everything else in this room. That's a pretty big number. About 10 to the 5 pascals. So if we were to build ourselves a vacuum chamber and cover that with a 1 square meter plate, the air in this room would be exerting 100,000 newtons of force on that plate. That's not a small amount. This is a rather large amount of pressure. In fact, you often will see kilopascals as a unit, as the standard unit instead of regular pascals. And in that case, room pressure is about 100, a little more than 100 kilopascals. This is one of those things where there is no industry standard on what unit should be used, though. You will see a lot of different units used for pressure. So let's just list some of them so that when you run across them, you'll know what they are. They're just different measures of ways of measuring pressure. So lots of other units. Let's go through some of them. 1 atmosphere. That's actually a really useful unit of pressure. Obviously, we just defined what it was, although obviously it wouldn't be a very good definition if it were just defined to be whatever the pressure is in the room that you're in right now, because that changes from room to room and even from day to day and even from hour to hour within the room that you happen to be in. So there is a true definition from this, which is 101.325 kilopascals. Is this always the pressure of, I just gave you the answer to this. Is this always the pressure in the air on the ground? The answer is no. This is a definition of 1 atmosphere, but this is roughly an average across the Earth, across time. It can change if you change in elevation. It can change from day to day as the weather changes. High pressure system moves in, it'll be higher. Low pressure moves in, system moves in, it'll be lower. But this is the definition of 1 atmosphere. It is at sea level, that's right. The average at sea level, that's right, ish. But again, define it to be that, even if it weren't, even if the average at sea level weren't exactly that, that is the definition of 1 atmosphere now. So we're stuck with it. There is the torr. Another word name for torr is millimeters of mercury, mmHg. Again, if you build a mercury barometer, a barometer is a tool to use to measure atmospheric pressure. They used to use mercury in these barometers, and the way they worked was the air pressure would push on the bottom and it would push mercury up into some tube, and the height of that mercury would tell you the pressure of the things of the air that was beating down on it. And so how high that went in millimeters was actually a scalable result. And so a torr is 1 millimeter of mercury in an old-fashioned mercury barometer. So the torr is defined, 1 atmosphere is equal to 760 torr. Oops, I forgot the 0. So another one you'll come across a lot is PSI. If you're filling up your bicycle tire or your car with air, PSI is the standard unit to use. PSI, of course, stands for pounds per square inch. Pounds per square inch. Obviously, not a unit that any physicist would be eager to use, because who wants to use pounds and inches for their measurements? But you should know about it because you'll run across it in your day-to-day life, and it is a valid unit of pressure. Why? Because you need force divided by area. Well, square inches is certainly going to be an area. Is pounds of force? It's a weight. Yeah. Is a weight a force? It is. Actually, pound is the English unit of force. It is not a mass. Kilograms are masses, pounds are forces. Pounds are the force that you're exerting on your scale. Kilogram is inferred by what the scale thinks the force of gravity is at the area where you're standing on that scale, and it does a little conversion for you to convert that force into a mass. But it has to be measuring a force, and it is a force. Does anybody know what the English unit of mass is? Equivalent to kilograms. It is the slug. The English unit of mass is the slug. So just be glad we're using metric units now. That's all I got to say. Any event, pound is a perfectly legitimate unit of force. Square inch is a perfectly legitimate, if crazy, unit of area. So this is a unit of pressure. PSI works just fine. So 1 atmosphere is equal to 14.7 PSI. So you'll also see it written LB per in squared, per IN squared, pounds per square inch, PSI. Okay, so I've got 10 minutes left. Excellent. So this is now getting to be somewhat old news, but does anybody know the regulation pressure inside an NFL football? Probably not. That's okay. This actually became an issue, it's probably 5 years ago now, in the famous Deflategate case. For those of you who don't know, this was 2015 in a playoff game between the New England Patriots and I don't even remember who the other team was now. The Colts, maybe? I can't remember. In any event, I'm gonna write it down. What is the regulation PSI? Again, you don't need to know this. It's just an interesting story, and it will get to another important. It will lead us to another important question, which I need you to understand. So just bear with me as we tell the story. We're getting somewhere interesting. NFL regulation football. According to the rules, has to be between 12.5 to 13.5 PSI. 86 to 93 kilopascals. So it was discovered that, so each team provides their own footballs to the game. And there's an official who goes before the game and checks them all to make sure they've been properly inflated. And at halftime, I guess Tom Brady threw an interception in the first half of this game, and the defending player took it back to their sideline, happy to have intercepted the ball, and noticed that it didn't feel like it was inflated enough. It felt like it was underinflated. The officials noticed, the other team's coaches notified the officials, who went in and measured all the other balls at halftime and noticed that almost all of them were underinflated by about 2 PSI. They were all at about 10 instead of 12 to 13. So this is Deflategate. You know, there's all sorts of excuses and gone back and forth, but apparently the less underinflated balls are easier to grip and easier to throw and more accurate or whatever. Anyway, cheating scandal, you get the idea. But what I want to come back to is the point of, look at those numbers. Does something strike you as odd about those numbers? 12.5 to 13.5 is the standard inflation for NFL football. Does anything strike you as odd about those numbers? It's below atmospheric pressure. Exactly right. What the heck is going on? And in fact, if you go and fill up your car tire or fill up your engine, your bike tire, you'll see numbers that are lower than atmospheric pressure as you're filling it up. Hopefully you get to higher than atmospheric pressure by the time you finish filling it up. But these footballs are supposed to be less than atmospheric pressure to start with. Dot? This is exactly right. They are not absolute pressures. When you, okay, so let's just, what's going on? We have been talking about absolute pressures. We've been talking about the absolute forces that a fluid would exert on a vacuum, on a plate that's covering a vacuum. When we're inflating a football, and we're inflating a car tire, or inflating a bike tire, or a basketball, or anything else, we are not measuring it against the vacuum. We're measuring it against the outside pressure. So really, what's measured, what we're measuring when we're inflating something like that is called the gauge pressure. Gauge pressure is the pressure difference from ambient. Ambient meaning the atmospheric. So absolute pressure equals the gauge pressure plus the atmospheric pressure. So when you are blowing up again, that pressure gauge that you're using is only measuring the difference in pressure between the inside of that football and the outside of that football. That is the gauge pressure. That's really all it can measure. It doesn't have any vacuums in it. It can't measure the absolute pressure. All it can tell you is how much higher the pressure is inside than it is outside. And that is not an absolute pressure. So you have to be careful about this. In fact, Neil deGrasse Tyson went on and gave some explanations about the temperatures and pressures and thermodynamics involved, and he totally forgot about this, and he had to make a correction of like 2 hours later when he went in, because he was thinking about absolute pressure. He was thinking that these were absolute pressures and they're actually gauge pressures. So don't be like, I mean, in all other ways you can be like Neil deGrasse Tyson, but don't be like that, like Neil deGrasse Tyson. Know the difference between gauge pressure and atmospheric pressure. So unless I specifically mention otherwise in this class, when I say pressure, I will mean absolute pressure. But just know that there will be specific times, even in this class, where the right thing to think about is the gauge pressure rather than the atmospheric pressure. And you just need to think about, am I thinking about a pressure difference between these two places, or am I thinking about an absolute pressure of forces being exerted by this fluid on something else? Okay, I have not going to start the next topic. That's a good place to stop for today. So I have a lab right after class today. If you want to pick up your exam right now, you can wait for me up there. I'll be up there. You can jump in and grab it. Otherwise, it will be until 4:30 tonight that I'm there, or I'll be around tomorrow afternoon, or Wednesday, or tomorrow morning, or Wednesday morning, or Thursday morning, or stop by sometime and pick it up if you'd like to.